Welcome to this physics tutorials. My name is Samuel G. Koidia, and I'm also going to proceed with the physics experiment and the physics practicals with respect to optics this time. I want to look at the focal length of a convex lens using a ray box. Now we have a couple of materials here that I want us to look at, and first of all I want to define those materials for you and describe them as you move along. Now you see the diagram somewhere there. In the first place, you must know what is this focal length. Now focal length is a lens is actually a special shaped piece of glass or plastic that will predict the direction of light. That's what lens does to ray. So now we have those two types of those lenses. You have this type that is thicker in the middle and thinner at the edges. That is a convex lens, and that's what we want to actually talk about here today. And that convex lens is also called convergent lens, because for convergent lens, rays that are close, we must just first of all define the part of this lens. We have the optical center, that is the part midway the lens, of course, and we have the principal focus, the principal axis, that's the line that is passing through the optical center. And we said the ray, the point where all the rays that are close and parallel to the principal axis will converge after refraction from that lens is what's called the principal focus. So the principal focus of this type of lens is going to be a ray focus. So now we have the principal focus, and we can be able to find the focal length. The focal length is the distance between the principal focus and the optical center. So we know U to be the object distance, that is the distance of the object from the lens, and you have the image distance, that's V, that is the distance of the image from the lens. It could be captured by the screen over there, and this is the object. So we are coming to that shape there. So I just want to give you the principles here. We say when all rays close and parallel to the principal axis, the point where they converge is what's called the principal focus. So that principal focus, the distance between the principal focus and the optical center, give you the focal length. So the focal length F is actually giving you this distance here. So we said there's a link between the principal focus, the focal length, the object distance, and the image distance, and that is what is actually captured into the lens formula. You have come across the lens formula, which says that the reciprocal of the focal length, this is this distance here, is equal to the sum of the reciprocal of the object distance and the image distance. This is what is called the mirror or lens formula. We run through this quickly. Now we have the ray box. We have discovered what convex lenses do to a ray. What they do to a ray is that they always converge the ray, because it is bulky in the center and the edge is thinner, so it's going to converge. That's why it's called convergent lens. It converges the ray, and now we have it's all convex lens in that case. So we want to find the focal length. That focal length is the distance between the optical center and the principal focus. That's the focal length that we want to find. And the object distance, I'll show you what's the object here just now, and the image will show the image. So I have defined the focal length which we are trying to find, and the object distance is the ones given to you. We see that now. These are the distances given is the U. So we want to capture the image distances on the screen as you move that. So now we go to the apparatus themselves. So first, this is the ray box. The ray box is going to produce the illumination that is going to illuminate the cross wire. The cross wire is the object. Now the cross wire is the object, so I go back to that. So if you look at this is the ray box, and you have these cross wires. These cross wires are going to be the object. So inside this box there is a lamp in there. That's the lamp, and now that goes to the electrical part of it. That's the connection somewhere there, and you have this lamp is going to illuminate the object such that the ray from this object will be captured by the lens. So now that is the ray box for you. That is the cross wire. This cross wire here is the object in that case. So the object is, so the ray box contains the object and also the light that is illuminating the object that is being copied. The light copy the object and bring it to the lens. So this ray box is set such that you can, but if you don't have this sophisticated ray box, you can also use the candle. You can use candles. You can see the candle now serve as the object and also the light you are looking for. The flame of the candle now will become on the object in that case. So now we have the ray box which contains that lamp in there, and that is a cross wire. That's the cross wire. So far you've seen the cross wire there, and now we are supposed to have an optical bench. We are supposed to have an optical bench, but in the absence of optical bench, we can also use a meter rule. A meter rule we solve the same problem, and we can call the meter rule a scale because it's a scale. You can use it as a scale. All of these are scales. We just call them rulers, but they are scales because there are scales on it. So I can call this scale or optical bench or meter rule, and then starting from 0 there, I'm going to 100. So we can, as the length can give us, that's 100 centimeters. So this one is serving as a meter rule, but we can use it as an optical bench, which is also just like this. So the same rule there. So now I have the screen. That is the screen there. That's the screen. That's watch stuff. You can, if you don't have this sophisticated type, you can use any paper in a white sheet of paper can serve as a screen there during the exam. So this is a screen. So you have a screen, and now we have the lens itself. This lens is thicker in the middle and thinner at the edges. This is the lens which is the convex lens. So I gotta label it for you. This is convex lens. This is the convex lens. Now that convex lens is this one here, but we are assuming that we don't know the focal length of this. We know the focal length already. We said it is the distance between the optical center of the lens, and the principal focus, where the light is focused. That distance is called the focal length. So we want to investigate the focal length of this. So that's what is the experiment. So this is the convex lens. We want to find its focal length, and this lens must be inside a holder. This is lens holder, so it's going to be like this. Inside this is a lens holder. So and that is it there, and we have the screen. We have the optical bench, which is also the meter rule. So now we are expected to find the position of the image. The object distances are already measured in this question. We have the object distance is 30 centimeter. So I'm looking at 30 centimeter. I start from 0 somewhere there. I go right there until I discover 30 here. So this is 30 centimeter. So this 30 centimeter, I must ensure that it is exactly at the 30 centimeter here. That 30 centimeter here on the meter rule is going to be at the optical center. So how do I get the optical center from this? Because the mirror, the lens is right inside there. The optical center is that line that is dividing that in the middle of that lens. So we can get it from here. That is why we have this line here. This line is the optical center. It's going through there. So you can use it that way, or you use this other line there. So you take note of this line. If it is not there, you can take your ruler and you draw that line right there, because that line is the center of the lens. When the lens is inside, that the center of that lens is that line. So that is the optical center. So now we have that. We can now, that is where your reading stop on the object distance, and that is where your image distance also starts. So this point is very important. So you can use some of the lens holders, we have them already. So you can, this is where your reading is taken. So understand that. So we have this. Now I'm placing it at 30. So 30 centimeter. So I'm going to place it at 30 centimeter. That is somewhere around here. 30 centimeter. I ensure that it is 30 exactly. And now one precaution I'm going to ensure here is to ensure that the object and the lens are coaxial. So that's one precaution. This is coaxial. They are in the same plane. As a matter of fact, they are in the same axis. The co means the same. They are in the same line. Axis is line. So they must be coaxial, meaning the object there and the lens and the screen must be coaxial. That's how I'll be able to capture the image there, and that's how this ray of light coming from that hole will pass through this lens, and this lens will refract it. So it has to be coaxial. And one important, another precaution you will want to take is that you must ensure that you capture a sharp image. Sharp image. So these two are very healthy precautions that you may take into consideration to ensure that you have accurate reading here. So sharp image. What's the sharp image? This may be relative, because to the eye of another guy, your sharp is something that is not sharp to the eye of the other guy. So that is where the practical is actually, the human factor comes into play. So now let's look at the experiment proper. Now we have defined all the parts, and we have this is it. So I will try to find, this is the screen. So some of the experiment, you are required to fix this object distance. You put it, let it be fixed fixed, so you don't move it, so that object distance becomes fixed. That's at 30 is there, and I'm ensuring that they are of the same coaxial with this. I have the, let me just so that you could see it properly. Now it is at 30 centimeter. This distance is 30 centimeter there. This whole rule is 100 centimeter. So I have got the object distance as 30 centimeter, that is in centimeter. So I'm also coming to take the image distance. So now this ray of light will be refracted by this lens, and it is going to be focused at a point where the image is formed. So we want to capture that point where the image is formed, so we'll be able to find the distance here to the image as the image distance. That's the V there. So now we have already ensured that the optical bench, and this is at 30, and the ray, the wire, cross wire, which is the object, is coaxial with the lens. So the experiment will tell you to now adjust. That word adjust is to move up and down such that you have a sharp image that is captured. The sharpness of your image is relative to some other guy. This is a sharp image. So how do I identify that the image is sharp? You see that this is a cross wire, and that cross wire is, when I go down, it disappears and become blurred. If I go beyond that, also it becomes blurred, so it's not sharp. So I'm going beyond that, but the sharpest part of it is somewhere there. So I got a sharp image somewhere there. So now that's it. So you have the sharp image as it is given to that is here. So now it is sharp. This is sharp. So you test and see at your own convenience. You know which one is sharp. So as I'm moving there, you see it become blurred. If I come closer to it, become blurred. So there is a point where it's going to be sharp. So that is a sharp image for me. So I can keep that sharp image somewhere there. So this is the sharp image, to be precise. So here, this is sharp. You see how the shape of the wire is becoming distinct there. That's what I could call a sharp image. So as you move from that, you see it become blurred. You see it become blurred. So you adjust to your convenience until you discover that it is sharp. So when it is sharp, you now see. So you can see that there are two things happening here. It's because the distance here, so if I keep increasing this distance, you will see that image size is going to drop down. So this is 30. So I should now read my image distance here. My image distance is from 30, or what I can read here is 93. Yep, so my sharp image occur at 93. From here, is there exactly at 93. So the sharp image is there. If I go backward there, you see it become blurred. I go forward, it become blurred. So the sharp image is somewhere there, and that is my on point of sharp image. That's 93 from the rule. If it was an optical bench, the optical bench is just the same as this meter rule. They do the same work. So now we have already got 93 somewhere here. So I need to find the image. This is the object distance, is U. That's object distance. Now this is image distance, V, somewhere there. So now I'm coming to find the image distance. So if this is this, so the image distance will be, of course, it is 63, because if I remove 30 from 93, I'm left with 63. So I got that for this. So I want to see whether that position is actually the position that will give me those two positions will help me with the mirror formula to now discover the focal length of this lens. So watch, this is the focal length. So I can have, let me have space somewhere there. So I use this formula to try to get what is going to be the focal length of that stuff. So now I have 1 over F is equals to 1 over the object distance is there. So you have 30 plus the image distance is 63. So if you do use your calculator, you go through here, you find out that the focal length is somewhere around 20 centimeter. So you'll be able to discover this. So if you do the math there, you find this, you get the focal length there. You use your calculator, you punch this, you find the LCM here, and you find this, you make F the subject of the formula, you get approximately around 20 centimeter. So now that is how you find the focal length there. So in the exam, you'll be required to now increase the object distance and see what will be happening to this image distance. So let's see what will happen. Is it that the image distance is going to be dropping? So we'll know. So let's see. So I'm moving this from 30, I'm moving from 30 now to 35. So now I move to 35 here. So 35 is somewhere there. That's 35. Yeah, so the object is at 35, object distance 35. Watch the size of the image also. Watch the previous one. That's now I'm trying to find the image
Yeah, so you have seen that it is now dropping somewhere. It has dropped to somewhere around 83. You see, when I go backward, it disappears. When I come forward, it disappears. So the sharp image is somewhere there. So this is around 84. So you read that point as 84. Subtract from that, this gives you 54. Right, so how did I get 54? This is 84 here. Do I remove 84? 84, sorry, it should be 84 minus 35. So 84, I remove 35 from that. This one is 4, this is 9, so this is 14, 9, and now we have, this is 7 minus that, you give us 4, so it's 49 in that case. So you have 49. So I'm moving. So now these two will move with the same idea. So watch what is happening to the image distances as I'm increasing the object distance. That is, as the object is moving away from the lens, this is the object. In this case, the two of them are fixed, and this is the one moving. So in another experiment, this will be fixed, this is fixed, and this will move. So in this experiment, we are fixing the ray box, that is the object, and we fix the object distance, which is the lens. So this distance is fixed, and now we adjust this to ensure that we have sharp image. That is just what I've done here. So watch the previous image, watch the size of this image as I'm moving away from this lens. Well, as I'm moving now, I want to go to 40. So if I go to 40, this is 40 somewhere here. This is 40. So I'm moving from here. So from here to here is 40 centimeter. So from that 40 centimeter, I'm going to find this sharp image. So it is blurred there. It is also blurred there. It is, so the sharp image becomes there. So you must be able to see that the sharp image, the image is becoming smaller as I'm moving, as the object is moving away from the lens. The image is becoming smaller. So you see that stuff there. That is what is happening here. You see there. And now this is the sharp image. So there, it is a sharp image. So it has dropped to 81. So it is 81. So 81 minus. So see how I'm getting that 81. So 81 minus, this is 81 minus 40. So I have 41. So if you like, you can be writing these numbers. That's how am I getting that 81? This distance is for 40 centimeter now, and here I read on the same meter rows 40, 41, 42, that's up to 81. So if I want to get this distance, is 81 minus 40. That's how I got this 41 here. That is the V. This is the V here. That's how the 41 comes. So it is not that 81 you read. So take note, students will normally make the error here. They will record the image distance as this number. It is not this number. It is this distance that is the image distance. So how do I get this distance? It is measuring this from this number here, from 0 here to 81. Then I measure from 0 here to 41. Then I reduce this 81 from this 40. This distance here is the image distance, which is the V. The 81 is not the V. Note that it is just subtracting the 81 from the 40. Now give you this distance. This distance is the image distance. That's the V. So this is the V. This is the V, as I told you. This V, and this is U. So whatever scale you are reading here, this is the object distance. But this number here, let's say in this experiment now, this last one, it was 81 here. This is 81. So it is this distance to here is reading at 81, and this other distance is reading at 40. So this was the starting. So now here we have U here. U is this distance. Now I want V. So if I want V, it is this 81 minus this 40, give me this V. That's how this V comes here. And now you'll be able to do the reciprocal. If you continue, let's see how we go down with more. Now I want to try 45. So 45 somewhere here. This is 45. So at 45, yep. So on 45, you see the image is becoming smaller. Still sharp, but smaller. It's dropping down here. So this is it. So it's smaller now than the previous one. So it's becoming smaller as I'm moving away. So you see the image dropping there. So now remember the concept when we are drawing the ray diagram. We saw as you increase as the object move away from the lens. That's how you see the image is coming closer to the lens, but it's dropping in its size. So you get that this is it here, so it's coming closer, but it is smaller. In that case, this is not sharp, this is not sharp, this is the sharp. So you see, when the wires, the cross wires becomes distinct, they will be able to know where else is sharp. So this experiment can be done in another way. You can make it complex in this case, where you are asked to also measure, let's say, the height of that image, which is this height of this image is h. The object, sorry, the height of the object is h. Let's say h there. That is constant, because the cross wire or the holes, the size of the hole is not going to change throughout the experiment. But the images here, as you capture them here, when you capture that image here, this image, the hole here, let's call it HO. So it keeps changing. So now you can also be asked to find the image, the object height and the image height. So now in that case, let's say I want to double it here. After getting the image distance, I still want to know the relationship between the object height and the image height. So I got my ruler somewhere here, so I can measure the distance between that is the hole, because the hole is the one that is visible somewhere there. So I can measure somewhere there. This is I read that distance here. Then I come back here. I use the same ruler. Let's say I use that scale. It was this scale. Yes, I use this scale here. So I found the diameter of the hole. The diameter of the hole. Then I compare this diameter to the diameter of this image. So I measure the diameter of the image there. So you find out that this image, this object distance, the height of the object is now bigger than the height of the image. So the experiment can come in this form too, where you are expected to measure the height of the, after finding the sharp, so you can be doing two things together. Now I've got the sharp image, that is my image position. But I want to see what's the height of that image with respect to the height of the object. So this is constant, so I'm going to measure the diameter. Each line, cross line here, if you want to take the vertical line, no qualms, you would measure it that way. Or you want to take the horizontal line, the same, the horizontal line you measure, that is the diameter of the hole you measure. So the experiment can be done this way too. So let me proceed further. I still go with, I'm increasing to 45, I've done 45 so far. So you have seen that. So you can go through this experiment, you can verify this experiment again by repeating it again. You can see as I'm moving the object now, if I'm moving the object towards, you see it's becoming bigger. So I can move again and the object goes, so I can go closer now there and I can move it becomes bigger as I'm moving there. So this is it. So you can get a control, so you can come back and repeat it if you like. So as I'm moving there, you see now I can't find anything because I'm now below the focal length. So if you do this, maybe you are now below the focal length. So when the object is between that focal length, you see there is going to be a difference, a difference in the observation. So check here. Now I can still repeat it again. I put it at 2. So and I see the, so let's say it's at 35. 35, watch that here. That is it here. So you can come and start all over again. You get 20 from the, you always ensure that the rule does not mix, does not move. That's 30. You saw how big was 30. That's 30 centimeter. You saw the image is bigger there, 30 centimeter. Now what about 45? So see 45 somewhere here. So 45 here. 45 it became smaller. So you see I've done extreme distances. So as you are moving away from the object is moving away from the lens, that's how the image is becoming smaller. So we have already verified that size of the image. So you can now do the math inside here. You can do the reciprocal of this, and you can also add them. Any question can come here now. You can also find the multiple, the product of the two, and you can plot a graph. Let's plot a graph of u 1 over v against 1 over u. So because of this, if you do this math, you find out that this was increasing and this was reducing. So there's going to be an inverse proportionality, and you know inverse graph, so it goes that way. So you see that as v was reducing, as u was increasing, the distance was increasing. That's how this v was reducing. So you get this type of graph. If you plot the graph
when you go through it, you see that you have this type of graph. And when you get this type of graph, now you come to find, you read this. Maybe you read this value somewhere, whatever value you get here, let's say 20, or you get this other one here, let's say 30. So these are arbitrary numbers I'm just using. So now let's say I get these two values there. So if you get the mean of those values, the mean, that's the average, you add these two plus that. Let's get to find that. Let's say you got 25. Now if you get the average, now if you take the reciprocal of this average, the focal length is going to be 1 over the reciprocal of the mean average, the average mean. So the average of that mean, yes, that's the mean average. If you get, that's another way you can find the focal length. If you cannot do a direct method there, you can plot the graph first. You grab the graph. When you plot the graph, of course those points are going to be extrapolated to cut the y-axis, and the extrapolated to cut the x-axis, that is the inverse u-axis and the inverse v-axis. When you extrapolate them, they must meet a number here. If you take this number and take this number, you find, since both of them are intercept, this is intercepting on the y-axis, this is intercepting on the x-axis, and we call them in this case the inverse v-axis, the inverse u-axis. So when you take the mean, that is, you add the two, the average, I mean, you add the two, divide by 2, that value here, if you take the reciprocal of this value, it will give you, let's say it was 20, let's say that's 20, let's say I got 20 here as well, so 20, so it's 20. So if you do the math, you find out that you have reciprocal of that one will give you the focal length as well. So it is just the procedure. First, you get the image and object distance, you find the reciprocal, that is 1 over 30, that is here, 1 over 63, that is here. If you plot that graph, this against this, you extrapolate the graph to cut the y-axis and the x-axis. Those two numbers, you find them in, that's you add and divide by 2. That value, you take the reciprocal of that value, will give you the focal length of this length. So it's easier that way. So you cannot see you can also test some of the concepts as you're moving along. You want to see what happens to the ray of light when it's moving away from this. So this is the diagram so far. So we want to see what will happen if let's say this was the lens. From the lens diagram, we know that already. Now this is the principal focus. This is the center of the center, which is twice of this. The C, it is 2f in that case. So now if the object is somewhere here, yeah, so what happens, this is it. So this is the f, and this is the 2f, if you like. Now you see that the ray of light will move from this and hit the center of the lens, and it will pass through, because we say it's a converging lens, the ray will converge, right? So it will converge, and it is going to converge, pass through the principal focus. You said it's the point where all the rays close and parallel to the principal axis will converge after refraction. And there's another ray that comes through the optical center, and that ray is going to be undeviated. That ray will not be bent at all. So that ray will now, you see something there. So it is going to be around here. So you can find out that this image is smaller than the object. That's what I was saying. If you draw the ray diagram itself, it's going to be very small, and it's closer. It's going to come closer to the lens. So the image is going to be, so look at the nature of that image. First, it is going to be a real image. It is real. That's why it's cut on the screen. Real images are cut on the screen. So that cross wire it was supposed to be upside down. Because it's a cross wire, you did not realize it was upside down. But if you use the candle there, you will see that it's upside down, because the flame of the candle, if this was the candle there, this is the flame of the candle. If you use candle there, here, when you find the image of the candle, it's going to be somewhere like this. The flame is going to be upside down. So on the screen, you see the flame of the candle, which was upright there. It now becomes upside down. You do not see the upside down nature of the cross wire, because the cross wire is already vertical line. So, but this is what happens. So I've just used an example here. When the two rays that are forming the image on the screen, one is passing through there and goes to the lens, and the lens refracts it. And we say that when the ray passes through the lens and is being refracted, it will pass through the principal focus. That is the point where all the rays close and parallel to the principal axis will converge
after refraction. Now there is another ray that passes through the optical center undeviated, and these two rays will meet somewhere and they will form an image that is inverted. First, the image is diminished, so you are seeing it as I'm moving away. It is diminished, it is real, and it's going to be diminished. Diminished means it's smaller than the object. That's where what you saw, it was small as I was moving, and it is real. It is real means it's going to be cut on the screen, and it is inverted. Very important, it's very inverted. And now you have to look at this diagram. So if you go back to your ray diagram, it's all the ray diagram that you went through in your previous lessons is what we are also trying to demonstrate here. So the focal length of this convex mirror can be found by those methods. So you try as much to see how you can actually understand it all by yourself. So I now give you a few precautions that you must take over. You must ensure that the object and the lens are coaxial. Very important precaution. And you ensure that you capture a sharp image before you read this point. You must ensure that it is sharp. It is not blurred at all, as we saw in the experiment. So that is what you can do. But in another setting, you can use the candle. So we can use candle here, but if we use a candle, we are going to see the flame of the candle not as upright. So that's why we said that the images formed on this lens is going to be upside down. So you will see, if you want to see the upside down nature, now if you use a candle, you see that the image of the candle on the screen is going to be upside down. That's telling you, it's verifying that this image is upside down, and it's going to be smaller as you move away from the lens. You see, as this is the object, that was the object, it was moving away from the lens, that's the lens. Now as it moved away, the distance was increasing. You found out that the object, the image distance was dropping, and at the same time the size of the image was also dropping. So you realize so many things here, and the rest now can be manipulated. We can find the sum of this and this. We can find the product of the two of them. Is all possible. So I believe that you have already interacted with this. These sophisticated materials, if you cannot find them, you can use candle. It's very important here. You stress on the candle, and you see actually the candle is very precise, because it can show you how the image is inverted, because you can see the flame of the candle upside down. So I want to thank you for listening, and we want to stop here, and we continue the lecture, the other lessons as we progress. Follow me and make sure you subscribe, and you see how we can get the other videos coming. So thank you for your audience.